Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMathInstruction. Today we'll be working on Unit number 9, Lesson number 2, on complex numbers. So in the last lesson, we were introduced to the imaginary number I and sort of the imaginary number system. All right, in this lesson, we're going to expand that a little bit by combining real numbers with imaginary numbers to create what are known as complex numbers. And let's jump right into that idea. All right, so a complex number is a very simple idea. You take a real number, all right, and you add it to a complex or to an imaginary number. Now, I just want to emphasize this, right? We remembered from the last lesson that I was the square root of -1. And this is the basis of all imaginary numbers, right? But granted, if I have I plus I, then by default, I have 2 times I, right? And if I have I plus I plus I have 3 times I. Now, these are also imaginary numbers, all right? So the idea here is that we have some real number, purely real number, and then we have some real number times I, which by default is an imaginary number. Okay, so we could have something like 5 plus 7i, and this would be the real component of the number and the imaginary component of the number. And the reason that we can't put them together is because you can't actually combine real and imaginary numbers. The best you can do is leave it as a real number plus or minus an imaginary number. But when you do that, you have a complex number. Now, technically, that means that all numbers that you know about are complex numbers, right? Because we could have something like 8, which is purely real, but we could still consider it a complex number because we would have this, 8 plus 0i. Or you could have -4i. This would be purely imaginary, but again, it could be thought of as complex because we could think of it as 0 plus -4i. All right? So that's all complex numbers are, putting together a real number and an imaginary number. Anyway, pause the video now if you need to, just to think about this a little bit before I clear out all the text. Now, complex numbers add, subtract, multiply, and divide. In this course, we're only going to look at how they add, subtract, and multiply. Division is a little bit out of our reach right now, but I'm sure that you'll learn more about complex numbers and their arithmetic in pre-calculus or your next course. So let's take a look at an example, very easy example, where we add and subtract complex numbers. Exercise 1. Find each of the following sums and differences. All right, now, the cool thing about this is that if I tell you to do letter A, and I don't show you how to do it at all, you're probably going to get the right answer. So pause the video and think about how to do this, and if you get the right answer, it means that you have a good sense for how complex numbers add and subtract. Okay, well, if you added the real parts and you added the imaginary parts, that is exactly what you want to do. Because we still allow addition to be associative, meaning we can get rid of all the parentheses. We also allow it to be commutative, which means we can group the real parts together, and we can group the imaginary parts together. And then -2 plus 6 is definitely 4, and 7i plus 2i is definitely 9i. And there's your complex number, your real part being 4 and your imaginary part being 9i. And that's it. And that's why we're going to do exactly one exercise, well, 2 exercises, involving the addition and the subtraction of complex numbers, because quite frankly, it's pretty easy. It's just like combining like terms. So do that for the rest of the problems, but be careful with the subtraction. You know subtraction is going to distribute over that complex number. So watch out for that. But pause the video now and see if you can do all of these. Okay, let's go through them. Real simple. This is addition. So really, it just means I need to add the real portions, which will be 20, and I need to add the complex portions. Sorry, the imaginary portions, which would be 3i. Now, subtraction is always dicier, and it doesn't matter whether we're working with complex numbers or anything else. But the plain fact is, when we distribute that subtraction, that 2 will become negative, and that negative 7i will become positive. So it's not all that difficult. 5 minus 2 is 3. 3i and 7i is 10i. And there's our final answer. Likewise with this one, negative 3 plus 5i plus 8 minus 2i. Negative 3, positive 8 is positive 5. Positive 5, negative 2 is positive 3. And there's our sum. Every answer can be put in A plus BI form. A plus BI form. You'll see that instruction a little bit, A plus BI form, meaning you've got a real component and an imaginary component. Anyhow, pause the video if you need to right now to write down any of this work. All right, let's do a real quick multiple choice problem, and then we'll move on to finding products of complex numbers, which are way more interesting. Exercise 2. Which of the following represents the sum of 6 plus 2i and negative 8 minus 5i? Pause the video now and do this quickly. All right. Well, the only thing you'd have to worry about in a problem like this is the difference between a sum and a difference, but sums are easy. 6 plus negative 8 is negative 2. Positive 2i, negative 5i is negative 3i. So, looks like choice 2. All right. Nothing to sweat on that one, I don't think, but a problem like that was to come up on a standardized assessment, probably look like number 2. But now let's get into products. Now take a look at this. It says find the following products. Write each of your answers as a complex number in the form A plus BI. Well, just like with addition, I'd like you to take a shot at this in letter A. Don't worry about letters B and C. Pause the video now and work on letter A. All right, let's go through it. Now, what I'm hoping is that you treated this almost like a FOIL problem. Okay, and by that I mean I hope you did 3 times 7, which gives you 21, 3 times 2i, which will give you 6i, 5i times 7, which will give you 35i, and 5i times 2i, which will give you 10i to the second. Now, some of this is pretty easy. The 21 is what it is. 6i and 35i is 41i. But then what do I do with this? I mean, it says put it in A plus BI form. It didn't say I could have I squareds left in my answer. But that's the beauty of complex numbers. You see, I isn't just a variable. I squared is negative 1. I don't know why I just put that in parentheses. I squared is negative 1. Always, 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 always. This is probably the most important thing about I. Maybe even more important than knowing that I is the square root of negative 1. Anytime I see an I squared, I'm going to replace it with negative 1, and we're going to see that repeatedly. But that means I can now combine it with this real portion. 21 minus 10 is 11, and I get 11 plus 4i.
Oh my gosh!
And it's a complex number. See, complex numbers don't have I squareds in them. They don't. They don't have I squareds, they don't have I cubes, they don't have square roots of I. It's A plus BI or nothing else. So given that method, why don't you try B and C? Okay, let's go through them. So we're really going to take it just like we're kind of multiplying two binomials, because we are. Negative 6 plus 4i plus 18i minus 12i to the second. I'll oftentimes combine these things first, 22i, and then whenever I see an I squared, I'm going to replace it with a negative 1. So that's negative 6 plus 22i plus 12. That's not minus 12 minus 1. It's minus 12 times negative 1. So I can now combine these two, and that's a positive 6 plus 22i. All right, let's do one more. 4 times negative 5 is negative 20. 4 times negative 3i is negative 12i. 1 times negative 5i is negative 5i. And I times negative 3i is negative 3i squared. Again, that negative 20 is what it is. Combine these two, we get negative 17i minus 3 times negative 1. Again, not minus 3 minus 1. That's where students make mistakes, is that they'll have something like this, and then they'll write it like this, and oh, it's negative 4. No, it's not. Right? It's actually a positive 3. And then that negative 20 and that negative 3 combine to be negative 17 and negative 17. That's kind of cool. Negative 17 minus 17i. All right? But that's how you multiply complex numbers. That's not hard either. Right? That's not bad either. In fact, we're going to play around with multiplying complex numbers a little bit more on the back side of the sheet. So pause the video now and write down anything you need to. Okay, let's get rid of the text and keep going. All right. Now, the multiplication of complex numbers is still fairly easy. So to take this up a level, to take it to a level where it's truly Common Core, let's take a look at a more symbolic problem. Exercise 4 says, consider the more general product, a plus bi times c plus di, where constants a, b, c, and d are all real numbers. So a, b, c, and d are just, normal numbers, however you want to think about it. You want to think about them as integers, you can. You want to think about them as fractions, you can. But they're just real numbers. Letter A says, show that the real component of this product will always be a times c minus b times d. All right? So the real component will always be given by this. Well, how do we show that? Pause the video right now and think about it for a second. Well, we're really going to do what we just did. We're going to have a times c, which is, a times c. Then we're going to have plus a times d times I plus b times c times I plus b times d times I squared. Okay, well, I don't know. A times c plus, you know what? What can I do with this? I'm going to factor an I out. I can do that. A times d plus b times c. And then every single time, I'm going to put in a negative 1 there. But that means I can rewrite this as a times c minus b times d. And I'm going to put that in parentheses. Because I can, right? Associative and all that. I times AD plus BC. But that means that this is the real component because it's not multiplying I. And that's what we were supposed to show. The real component is A times C minus B times D. Now letter B is interesting. It says show that the product of 2 plus 3i and 4 minus 6i results in a purely real number. Okay, well, try that. See what happens when you find their product. Okay, well, let's go through it. A purely real number. We'll stick in red here. 2 plus 3i times 4 minus 6i. I could have sworn there'd be an I component. Well, let's take a look. 2 times 4 is 8. 2 times negative 6i is negative 12i. 3i times 4 is positive 12i. And 3i times negative 6i is negative 18i squared. Well, these two cancel. So I'm going to get 8 minus 18i squared, but that still looks like it could have an imaginary component. But as soon as I put in a negative 1 in for I squared, then I just get 8 plus 18, which is 26. And that's purely real. Right? There's no I component. Purely real number. Now letter C, I especially like this one. It says, under what conditions will the product of two complex numbers always be purely imaginary, a purely imaginary number? How in the world will this product ever be purely imaginary? I want you to think about that, and as a hint, think about this expression. That will help you out, okay? All right, let's talk about it. Well, in order for it to be a purely imaginary number, the real component must be equal to 0. Well, that means that a times c minus b times d has to be 0. Well, there's your condition. And that could be written in a lot of different ways. That's a good way to write it. You could also say a times c would have to be b times d. That would work, right? And it says, check by generating a pair of complex numbers that have this type of product. Well, try that. See if you can come up with values of a, c, b, and d. Okay, don't make them trivial, but a, c, b, and d, that then when we do that product will give us a purely imaginary number. All right, well, here's a fun one. What I would do is I would just say, well, let me come up with a product. Let's say a times c is equal to 12, and that's b times d. Let a be equal to 2. Let c be equal to 6. Let's let b equal to 3, and let's let d equal 4. That'll work, or at least it should work. So what would that mean? Let's see, 2 plus 3i, right? So a plus bi times 6 plus 4i, c plus di. Let's try it. We get 12 plus 8i plus 18i plus 12i squared. And you can probably already see it. That'll be 12 plus 26i plus 12 times negative 1. And that's going to be a positive 12 and a negative 12. And that is going to leave me with a purely imaginary number. Isn't that kind of cool? So it's weird. You can multiply two complex numbers and get a number that is complex with both a non-zero real and imaginary component. Or you can multiply two complex numbers and have things cancel so that you end up with just a purely imaginary number, i.e. some real number times I, or a purely real number, i.e. just some real number and no I component. All right, pause the video now and write down anything you need to. Okay, let's clear out the text. Okay. Exercise 5. Determine the results of the calculation below in simplest a plus bi form. All right. There's nothing new here. I would like you to pause the video and take a shot at this. All right, let's go through it. It's not that bad. You just have to be careful. Let's take this one first. I'm not going to even worry about that. we'll do 5 times negative 3, which is negative 15. Here we'll have a negative 6i. Here we'll have a positive 5i. And here we'll have plus 2i squared. All right, now I'll deal with this, because this is a plus here. All right, 4i times 2 is 8i. And then 4i times 3i is plus 12i squared. All right, now how you decide to start collecting things is up to you. What I'm going to do before I deal with collecting the i's is everywhere there's that I squared, I'm going to put in negative 1. And that happened a couple times. And then one more thing I'm going to do before I combine i's is I'm just going to make these things into stuff like minus 2 and that into negative 12. All right, let me combine my real numbers. Let me circle those in red. I've got negative 15, negative 2, and negative 12. So that's negative 27, negative 2 is negative 29. Let me circle the imaginary ones in green. Green, green, green. Negative 6 and positive 5 is negative 1. All right, that's actually a plus 8i. It almost looks like a negative 8, but it's not. So that'll be plus 7i, right? Negative 1i plus 8i plus 7i. Negative 29 plus 7i. Pretty answer with all the colors. Okay, take a moment, write down anything you need to, and then we'll do the last problem. Okay, clearing out the text. All right, exercise 6. Which of the following products would be a purely real number? All right. Well, we could certainly look back at exercise number 4 and work on that, or we could just start multiplying things out. Now, in order to have a purely real number, right, what really has to happen is all the terms with just an I on them, not an I squared, have to cancel each other out. So you really don't have to do the full-on multiplication. You only have to check those terms. So pause the video now and see if you can do that more efficiently than multiplying absolutely everything out. All right, well, let's take a look. What I mean by that is that if I multiply these, I'm going to get 6i. I don't like the green. I mean, it's okay. Green can make a guest appearance, but right, I multiply those, I get 6i. I multiply those, I get negative 4i. Now, that'll be 2i. I will have an imaginary component. Let's look at this one. Here I'd have negative 2i. Here I'd have negative 12i. Yeah, that definitely is going to give me an imaginary component. Here I'm going to have 10i. And here I'm going to have negative 10i. Oh, those are going to cancel, and I'm going to get something that is perfectly real. Choice 3. All right, pause the video for a second and write that down, and then we'll wrap it up. Okay, let's clear out the text. All right, so today we expanded our number universe to include complex numbers. And these are one of the largest classes of numbers because everything you've ever learned about falls within complex numbers. Complex numbers is just basically saying, look, any number can be written as a real number plus an imaginary number. Now those two numbers, they can't combine. Reals can't combine with imaginaries. And that's very different. Like rationals can combine with irrationals. Granted, it gives you an irrational, but whatever. But you cannot combine like terms between real numbers and imaginary numbers. And therefore, we write numbers like 5 plus 2i, which has a real component, 5, and an imaginary component, 2i. All right? You'll get more work with these as the unit goes on. But for now, let me thank you for joining me for another Common Core Algebra 2 lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.